MIT in the Department of Civil and Environmental Engineering, and among numerous research topics, he worked on hydrology and ecology of tropical peat forests.
Okay, well, thank you. And I first want to thank the organizers and the conveners for enabling these 2 weeks in physical and intellectual paradise. It's been great up until this moment. So I am going to talk about a tropical peat swamp forest. I'm going to use it in part to introduce processes and concepts of wetland hydrology and ecology. But I am going to focus on a field site where we've worked for 15 years or so, so the particulars of this one forest. Now, I've been interested in this for quite a while, really for two reasons. One is just the scientific curiosity of how these beautiful forests form, how they function, why they exist at all, why they exist in some places and not other places. And then another motivation of mine was basically to contribute to doing something about fighting climate change. Almost all of these forests have been cut down and drained and are now emitting enormous amounts of CO2 to the atmosphere. So by understanding the processes that occur in them, the processes that form them, the hope, the intention, and I think it's starting to work out, is that we can manage them to reduce greenhouse gas emissions. Now, I don't know if any of you heard that John say, I'm going to give another talk today. So today is not paradise necessarily, but at 4 o'clock on previous efforts I had starting a geologic carbon capture and storage business, and basically why that is not a good idea, but we continue to pursue it because of the efforts of fossil fuel companies. This is going to be very different. I'm going to talk about carbon fluxes in and out of the earth due to plant processes and degradation processes. Now, when I say a peat forest, it's just a tropical forest, but with 50-meter high, magnificent trees. But when the parts and pieces of those trees fall to the ground, they don't decay, at least don't decay at the same rate that they're falling in. So organic soil is formed, that's what peat is called, and these big mounds, they don't look like mounds, but whole landscapes of 100% organic soils, which are composed of huge pieces of wood and kind of a matrix of soupy material that quite honestly we don't understand what it is. So these things store enormous amounts of carbon. They form over thousands of years. And the real fundamental reason why they exist, there's a lot I'm going to get into all the sort of subsidiary questions of this, but is that when the soil is saturated with water, the diffusion rate of oxygen through water is low enough that you don't get enough oxygen in there for microbes to decompose it at as fast a rate as new material is being added. But it's that new material that's being added that blocks the discharge of water from the forest, right? So it's sort of this complicated chicken and egg kind of conundrum in that the peat itself blocks the discharge of water that enables the peat to exist and continue to grow. Okay, we've had all kinds of, I want to start by saying, really I'm not responsible for any of the good or bad stuff that I'm going to talk about. Alex Cobb is a research scientist who's been working with me from the beginning, and we're going to look today at mostly his work. Allison Hoyt was a graduate student with me, and we're going to see a lot of results from her work. And Renee Demain is currently a postdoc working with our program. I realized I didn't put references throughout this, So I thought I'd just you throw this up so if it's videoed, someone can go and look at this. Almost everything I'm talking about comes from these 7 papers. Okay, so where is our study site, and how indicative of it is other places. So what this map is showing is someone's interpretation of the black areas here on the land in Southeast Asia that are tropical peatlands. Our field site is in the little country of Brunei, a wealthy country, and hence hasn't cut down its peat forest like everywhere else has in the last 10 or 15 years. It's on the north shore of Borneo, which actually contains 3 countries, and is about 50% larger than France. I just looked that up. Okay. I think a good way to start is with a little bit of history, and kind of this remarkable scientist, Dutch, Elizabeth, I don't know, do we have any Dutch people here who can pronounce this kind of nickname? What? Betcha, okay. So she was studying peat in the Netherlands, escaped the Holocaust by moving to Indonesia to study tropical peat. And no, not quite so smart, because then she was captured and put in a Japanese internment camp. But the Japanese, and I'd be interested to know why exactly, gave her the freedom and the materials she needed in that internment camp to keep working on her research. And she figured out some things that now seem sort of obvious. One of them was by looking at pollen in the plants and trees growing on the peat and in the peat itself, doing palynology. She proved that the peat is made up of the same plant material that's currently growing on it. But she also sort of worked on a lot of the fundamental concepts of why peat exists. She described that it's ambotrophic, rain trophic. And the importance of that is that all the nutrients that come into the peat only come in with the rain. There's no groundwater flowing in or river water flowing across it that brings nutrients from mineral soils or anywhere else. That it is in fact anoxic and uniformly very low pH. So all 3 of those things work together also to keep the peat from decomposing. And then we jump ahead. I don't think all that much work was done since she did it back in the 40s. We jump ahead to a paper by Sue Page, who's a UK scientist. She published some work 20 years ago now, showing that the peat fires that happened in 1997, because the drainage was beginning then, emitted enough CO2 to actually be a pretty large component of all of the anthropogenic CO2 emissions. And this is just from Southeast Asia. So the point here is people realize it's a large part of the carbon cycle, not just the carbon cycle, but anthropogenic perturbations to it. Okay, so I said, God, I hate this. I said that peat grows in domes. So here's actually a figure I stole from Sue Page. The slope of these things is about 1 in 1,000. So it's not a dome you're going to even notice. But what I want to point out here is her interpretation of the water table. And I thought it was wrong at first because she has the water table above the surface. It should just run off. But I'm gonna sort of explain that this is actually a good way to draw it, I think. Just to sort of orient us in length scales and things here, these are these big trees. There's a person, and you have maybe 4 or 5 meters of saturated peat with an impermeable layer underneath it. And then the water table under natural conditions oscillates between slightly above the surface to, and usually above the surface, to maybe 50 centimeters deep. And all of the action, the dynamics I'm going to talk about are in here with the oscillating water table.
Charlie,
yeah.
Tell us a bit how old the peat is if you go all the way to the bottom.
Yeah, so we radiocarbon date it, and the radiocarbon ages increase more or less linearly to the bottom where it's about 3,000 years old, which is because it was formed at the beginning at the drop from the last sea level high. As the ocean went out, you moved from mangroves to inland freshwater swamps. This is just a picture of what it looks like near our field site. And just to be clear, I'm going to show you lots of beautiful pictures of tropical forest. Most of the peat looks like this. This is an area in South Kalimantan that's 100 kilometers by 100 kilometers. The Indonesian government drained it to grow rice when the price of rice was high, then found out that rice doesn't grow on peat, and now there's this vast area, something along the size of Corsica. I think I looked it up, maybe even bigger. That is just devastated land, smoldering land, and well, no one really goes there. So that's what's happened to a lot of it. And the reasons are that it's drained. It's not so much that the forest is cut down, but there's just these extensive networks of drainage canals put in to both transport trees out of by deforestation and to drain it enough so that you can grow things on it. Not rice, but palm oil for the most part. Here's some work we did with the satellite, just sort of proving the point of what the palm oil plantations and their drainage does. If we just look at one little satellite tile here near our site. So this is a satellite that measures, it doesn't measure the elevation very well, but it measures the change in elevation between satellite passes. What this map shows is in that tile, these purple areas here are palm oil plantations, and you can see the rate of subsidence, the rate that the land surface is going down is high there. And this isn't because of compaction, this is because of oxidation of the peat becoming CO2 and going into the air. This is just a picture of sort of what the fires look like. They're weird, you can walk around on them. There's incredibly interesting dynamics of how these fires kind of spread and move underground. But it's a very low temperature fire, cool fire, which is bad because it means that the oxidation, the combustion products are weird. Things like benzene and other carcinogens come out of these fires. And estimates are in the bad years for fires, which now correspond with the El Nino cycle, tens to hundreds of thousands of people die. The epidemiology attributes it to the smoke. There's just a picture of the smoke coming from Sumatra and blowing across the region. Okay, so now I want to introduce you to the field site. And kind of what I'm doing here, let me say the first part of the talk, I'm kind of all over the place showing you pictures, trying to give you a context. For the second part of the talk, which is where you get your money's worth in a sense, becomes mathematical. So I'm not there yet. But here's a picture of where our field site is. It's kind of dark in here, but we found this area in Brunei where it hasn't been cut down. This is the border with Malaysia. The forest is gone there. And this is kind of fun. This is give you a little bit of feeling how you work there. We get to the edges of these peat domes by, pushing up rivers. This is actually worse than it looks. We can talk about that later. And we've built large eddy flux towers, which I'm not going to talk about here at all. And that's challenging because there's no way you can have a road or power or anything like that. So we have to hire these sketchy helicopters to drop in large amounts of stuff. We've even dropped pile drivers in. We bought over several kilometers of old oil pipeline and had to drive it in to create the foundations for stable eddy flux towers, which raises the question, if it's so hard to get the tower to stand up, how do the trees stand up? Yeah, so this is what it looks like. And I want to show you some pictures taken from the top of one of them.
How tall is this?
That's 65 meters. So we have two, and I'm going to talk mainly about this area. This is a pristine area, and this is what it looks like. So these are 50 meter, 55 meter high trees, but it looks like a cornfield, right? There is a dome under there. I'm not going to talk so much about this. This is a site which, don't tell the Sultan of Brunei this, is not pristine because an international company came in here and cut down all the trees, but it's listed as pristine, but it's not drained. Just some nice pictures from the top of the tower. I'm sorry that I don't know how to make it brighter. You can see.
We can turn off the lights. Can you turn off the light, maybe? Anybody know?
I can try.
Oh, yeah, it's okay.
That's good.
Oh, yeah, okay, that's a little better. Great. Let me just, this is standing on the forest floor. This is the kind of thing that Maciek and I should talk more about. For some mysterious reason, there's a monoculture of giant trees. And then let me show you this. These are the Shori albida trees. And then there's a forest that's sort of more the European or American height that grows under it, which has the typical diversity of Borneo. Yeah, actually, how do the trees stand up? So it's all anoxic under there, so it's really, I don't suspect there's any reason to put live roots too deep other than structural, but they hold hands. And we've calculated the wind shear and all that kind of stuff, and by holding their roots together, the whole forest can, to an extent, stay up. Now, remember I said it was ombotrophic? One little observation you make when you go there is a tremendous number of carnivorous plants. Not the big ones that grab you and eat you, but the ones that suck in insects, which is a little bit of extra nutrients transported in from the outside. And so I just want to give you a feel for sort of what the forest floor is like. It's a little bit of an attempt, not by me, because I can't do anything while walking through here. It's very difficult, very slippery. There's no defined forest floor. There's big gaps. I've been talking to a graduate student, and she just plummets, and all of a sudden her head's down there because she broke through some root or something and fell into the peat. Here is, kind of just threw this in here. Here's pneumatophores sticking up out of the peat. Presumably, pulling in oxygen to the pandanus, but after the discussion last night, maybe also releasing methane to avoid cavitation. But it's another indication of saturated anoxic conditions. Okay, why is the water table above the surface? Well, the question is, what is the surface? The surface is like insane. There's just huge all over the place. The way that we and everyone else defines the surface is as the low places. So it seems like the sort of underlying, actually formed amorphous peat has a good surface. And that's why we can put the water table above these low places. But there's plenty of logs and things sticking up out of it. What does the peat look like? Well, I told you it's lots of wood. I honestly don't know how much of that wood is roots and how much of it is trees. I know that when trees fall, they hammer in all the small trees like nails, so we find vertical trees, and all sorts of different interesting things happen. One thing, if you've ever done sedimentary geology, I think is a good way to look at this. This is a high energy deposit. It's very poorly mixed, fine grain and large grain. But when you're in the forest, it is low energy, like it's hot, but nothing's happening really fast. So how does this happen? Well, basically trees do fall over. Lightning strikes, kills a whole group of them, and they fall over. And when that happens, you end up with these tip-up pools. And then these tip-up pools fill incredibly fast with new organic material and disappear. But the stuff that falls into them is wildly disordered. And so if we look at sort of how this works over time, we can calculate that a lot of the peat is this tip-up pool filling. And one sort of cranky point I want to make about this is don't believe anyone who takes a core and interprets it as like a deep ocean core or something like that. This refilling happens after the peat is formed. Now, for the fun of it, I think I told someone earlier in the week, I just want to show you, this has no impact. Certainly on the mathematics that's coming. We had a camera traps out there recently, and we found a lot of a lot of animals that have seen us, but most of them we haven't seen. So we have bears, clouded leopards. Does anyone know what this is? It's a mother and a baby. Or not big baby. It's a tarsier. Look it up on your phone. Not now, because you got to listen to me, but later on, it's the most incredible animal. These huge eyes, and it leaps from tree to tree catching birds. Pangolin, which has been wiped out. I could talk, anyone wants to talk about this, every one of these animals has a story. But the point is, it's sort of a little bit of a conceit now among people who work there, but we start articles by saying, oh, peat swamps are actually really diverse. Because this ambitrophy in the past led people to say, oh, there's really not much diversity there because diversity is limited by nutrients. I don't know, you tell me. But in animals, I don't think they're. Okay, so one more animal here. I thought this was fun. Peter, is Peter still here? No, he's gone. Peter introduced the concept of groundwater fishing, and we do that. So here's a picture of fishing in the ground. So here we're cutting holes in the soil, putting fish traps underground, and then in this case spreading a net over here just to prove the point that the fish don't walk or fly to get into these fish traps. And okay, stop that. Okay, I'm really annoying. So some of us have talked, so this is basically the end of this sort of slideshow part of the talk. So the next whole section, stop it, the next whole section is, I want to describe to you, basically prove to you that the Poisson equation is all you need to do. You can do all kinds of interesting, elegant things with that to explain all of the fluxes and the shapes of the peatland, peat forest. But what I want to do here is introduce to you Le Poisson, who is who lives in the soils, in the solid material of the peat. And we don't know much about this. We know that it's sort of at the top of a food chain that begins with methane. But clearly there's a lot of them, and they must be moving around through, I guess we could call macropores, which has an effect on the transmissive properties of the peat, ultimately effect on its geomorphology, its hydrology, and everything else. The one point I want to make to you is whenever we talk about animals in the context of a conference like this, people find it funny. In my experience, every field program I've done, sooner or later an animal has turned up to be very important. Whether it's gophers, water flowing down gopher holes in arid regions accounting for all of the infiltration, or terrestrial crabs digging holes. Anyway, it's an interesting point to pay attention to the animals. Now, in this next section, I want to sort of address this conundrum of, it's a kind of just a way to structure it in which came first. So chicken and the egg thing, how is it that the peat accumulates when it's the accumulation of the peat that's necessary for keeping it saturated? And I think a lot of us in the room appreciate that when you have this sort of feedback like this, you end up with some pretty interesting science, actually. Okay. To start that, I want to show you 3 empirical results. I want to show you that the rate of decomposition is a very nice linear function of the water table depth. I want to show you that the hydrograph, the groundwater hydrograph, is universal. What that means is that in every part of the peatlands, it responds the same way to rainfall and drainage. And it responds the same way regardless of the antecedent conditions to different storms and drainage. And then finally, and this is where we get back to the Poisson, the surface of the land surface has a uniform Laplacian, a uniform curvature. Okay, so the water table controls the peat. Just to show you Oh, this is a fun thing. You can walk. We have two places where we have a kiloton of a kiloton. Okay, a kiloton of batteries. It's true in two places, and you can build a structure and put that in it. But I can walk around with the giant PVC pipe and just poke around until I'm able to stick a 6-meter well in by hand. I just have to thread it through all the wood underground. So we end up with all these wells. We can measure these hydrographs, and we can measure CO2 coming out of the peat with something that a lot of you would be familiar with here, just a device to measure CO2 emissions. Then we get stuff like this, and all the scatter in here are sort of hourly measurements, and really fascinating, interesting things happen diurnally, which I don't understand at all. But when you average over 24 hours, it's very consistent. And I don't understand why that's the case either, but it's true. And for what I need to do, knowing that a 24-hour average of CO2 emissions is a beautiful linear function of water table depth is all that I need. So one sort of simple calculations we can start to do right away with this is we can say, well, here's the water table over a year. What are the carbon fluxes out of it? So when the water table is below the surface here, we get these big CO2 emissions. When it's above the surface, we get a lot of flow carrying 60, 70 milligrams per liter of organic carbon. So we look at a histogram of where the water table is. It's actually mostly in the top 10 centimeters above the peat surface. And that's kind of where the minimum of the organic carbon fluxes out of the system are. This makes it seem a little bit easier than it is, but I think it's a nice sort of elegant thing. Okay, now the hydrograph is universal. It's just showing to do this, we need to measure rain, we measure some stem flow, and that kind of thing in order to construct these hydrographs. And let me explain. I don't know why I did. Okay, so here's the kind of thing we measure. This is millimeters. And this is measured over about a month or more. Each one of these little drops here when it's not raining is just the transpiration from the trees and plants during the day, and then at night not much happens, maybe a little condenses. But each time it rains, infiltration is essentially instantaneous, and you just get this big jump up in the water table. Now what I can do here is try and explain to you how we construct this sort of universal hydrograph. So if we just take periods of time when there's a recession, the water level is falling, and slide those things all around until they overlay in one curve, what we find is, well, it does overlay in one curve. So it's always behaving the same, and then mixing up wells sort of all over the place in the peatland. So we end up with something like this. These are the recession curves. This is not plotted versus time, but it's the rise as a function of the rainfall depth, the number of centimeters that fell. There is an exception here. But there's an exception here. And this bothered me. But what I want to convince you of here is that this is in fact the exception that proves the rule and is really useful for understanding things. Okay, the third empirical result is that the surface has this uniform curvature defined by the sum of second derivatives in orthogonal directions, right? The Laplacian. And we can try and measure this, with theodolites, but fortunately for some reason, someone paid the huge amount of money to do LiDAR there, and we were able to get hold of it. So we can do it from airplanes. And what we find here, here's our peat dome. A lot of the stuff I'm showing you are measurements that are taken in here. What we find is this surface topography that does have a uniform Laplacian. We actually, the history of this is we had no idea. We did this and then we found out that that was the case. Now, it's kind of insane to go to a tropical forest and try and measure second derivatives of the land surface. Totally insane. So how do we do this? Well, I wish I had a picture of Jennifer showing Tomas's talk, right? Remember that? Because one thing on that was the divergence theorem. So what we can do is say that the integrated Laplacian in some area is in fact calculated by the integral around the perimeter of that, of the normal gradients of the surface. We're not talking about pressure or head, we're just talking about land surface here. And in fact, if we differentiate this with area, we can do this clever thing where we take a groundwater flow tube, in this case starting at the very middle, along the edges by definition, there's no gradient, and there's no end, there's no length there, and then just measure the gradient across here, and in that way we can back out the Laplacian without the incredible statistical problems you have if you just try and do it in the brute force way. So why would a landscape have a uniform Laplacian? I think to give you a little, oh, David knows, but some of you might not. Does everyone know? No, okay. Well, here's a couple examples. So the tops of some hill slopes have uniform Laplacians, and it's been used to describe the polar ice caps as well. I'm not quite sure how accurate that is, but it has been used that way. So the basic theory is that if you have a hill that's subject to tectonic uplift at a constant rate, and what do you call it, the creep of the material, this isn't water flow, this is material flowing, is proportional to the gradient of the hill, and it's at an equilibrium, or a steady state, or whatever you want to say, then what we can write here is, did I do this? What did I do here? Yes, the two are balanced, so this is the uplift minus the rate of loss, and of course that rate of loss is a derivative. We plug that in, and we get a Laplacian, and just rearrange it, and what we get is that the Laplacian is the ratio of the rate of uplift to the parameter that describes linear creep. So is there something like this for a peatland? You might think at first not, because the peat's really not moving as far as we know. But this is where the hydrology comes in. So here I've written Boussinesq's equation. So it's saying that you have a storage, a specific yield storage here, and the water table elevation, or the head, changes with time. The specific yield gives you the amount of water related to a change in head is equal to the discharge plus some atmospheric input, i.e. rain, but minus evapotranspiration. And one thing I realized here is the S and the T here are dramatic nonlinear functions of H. So one terrible thing that hydrologists do is they call those parameters. They're actually, that function itself is perhaps the most important thing here. So let's do a few things to this equation. First of all, let's write it in terms of depth to the groundwater table from the surface rather than the surface. So if we do that, we just plug in for H everywhere there. We can simplify it after doing that. The rate of peat growth and loss is very small compared to all these jumps up and down with rainfall. So this term is negligible. But on the other side, we have this universal hydrograph that says the depth of the groundwater table is the same everywhere. So these don't have spatial derivatives. So we can simplify it by taking out the actual position of the position in space and just use the same depth everywhere. And that leads to a somewhat simpler equation. But we can go a little further. Well, we know this is uniform, and I'm going to have to wave my hands around. I'm going to come back to convince you of this, but I'm going to, right now I'm going to argue that S and T are uniform. Just from a simplest zeroth order, look at things, there's no reason to think they wouldn't be. Everything about the peat is the same everywhere. If you were dropped down anywhere in the dome, you would be lost. You can't figure out where you are. It's the same plants, the same texture. So there's no reason to think they're different, but I am going to come back and prove that. And because transmissivity we think is more or less uniform, my gosh, okay. Oh yeah, okay. Well, because these two things are uniform, this has to be uniform, right? And now if we pull the transmissivity out of here, this term is uniform, this part of the product is uniform, this is uniform, this has to be uniform in space also, and that's the Laplacian. So that's sort of the physics behind this observation that the Laplacian, the curvature of the peat surface, is the same everywhere. Okay, I want to give you 3 interpretations. Where am I on time? I have no watch.
55 minutes.
I've gone 55 minutes, or I have 55?
You have.
I have it, excellent, okay. So 3 interpretations of this uniform Laplacian. The first is just very qualitative, sort of useful way to think about peatlands, and that is that they're self-healing. So if you have, say, a parabolic peatland, which has a uniform Laplacian, if you dig a hole in it, it's like one of those tip-up pools, it fills up right away and the hole goes away. If you were to, say, take that peat and pile it up somewhere else to make a bump, okay, now its Laplacian value has changed dramatically, as is the case here, but in opposite directions. It's got much more curvature. This oxidizes and goes away. So the peat is always working towards this kind of curvature. Okay, I'm going to give you 3 interpretations, and the third one is the hard one, but really the most important one. But these are very useful too. And that is what I might call the hydrologic interpretation. So here's the ODE that we derived to reach the conclusion that Laplacian is uniform. Okay, now we also, what I would like to do here is to look at how this behaves over long periods of time. So I'm going to average this over time, and I have to average over time, you have to point this right here. Take the expected value of it, or average over time. Of course, the water table goes up and down, so average over time is 0. And then we get the average of this and the average of this. So the Laplacian is equal to this, which should comfort you. I'm not quite sure how useful it is, but the point is that Laplacian is larger in magnitude. The peat dome is steeper, bigger, contains more carbon when the average rainfall is more, but it's flatter, there's less of it when it's very transmissive, so the water flows out of it easily. So in some technical sense, this mean transmissivity is a statistic of the rainfall, right? It's a convolution of the whole time series of rainfalls in some complicated way. That is really difficult to figure out. So this is comforting in that it makes sense, but not terribly useful. And let's see if any ecology-minded people are here. Something is really unsatisfying about this. Something's left out. Does anyone have any, like it seems, yeah, we're missing all of the ecology in biology. Surely it matters if the trees photosynthesize more or the bacteria which turn it into CO2 underground move faster. That's got to be there. Okay, it's not showing up in here because we're sort of assuming, well, it just doesn't show up in this formulation. So where is it? Okay, I showed you before that the rate of CO2 release is a linear function of the depth of the water table. I would like to tell you it's that easy, but when we talk about the overall net accumulation and loss of peat with the depth of the water table, it's not so simple, because we have to account for all kinds of things growing into it, trees falling down, maybe oxidation that's more complicated happening up in the, above the soil or something like that. But let's just guess that it's also going to be linear. And in fact, this is a bunch of data from people who tried to sort of calculate this from directly from measurements. So, but let's start with that and sort of see if it works. So then we have an equation here, not for the depth of the water table, but for the elevation, z in those equations of the peat surface. And so it accumulates at a constant rate, according to this model, and then is lost, again, proportional to the depth of the water table. This term is important because we don't want the intercept here. We know it doesn't go through zero. Now, at equilibrium, if I can use that word, this has stopped changing, it's stopped growing, say. We get this ratio that looks quite similar to what we saw, say, for hill slopes, where the rate of accumulation over the parameter, the steepness of the linear decomposition, gives you the average depth of the water table. So that's useful, but what is it now the Laplacian's not here? Okay, so this we have to do kind of implicitly. So we just showed that. This is the ODE that we derived. And if we want to find D average, D bar, such that this is true, that's going to be given by one value of the Laplacian. D bar is a monotonic function of the Laplacian. To find it, you have to do it computationally, because this is the same ODE, just written in a different way. This is very nonlinear because of these terms. So you could adjust the Laplacian. Yeah?
Charlie, the transmissivity doesn't have a D in it, or a version of D, Z minus D or something?
It has a D, yeah, that's what this means,
no,
D.
The calculation of transmissivity itself.
Yeah.
That's my question.
A D meaning depth of the water table?
Yeah, or the
Oh, yeah.
depth of the flow, of the cross-section of the flow to calculate transmissivity.
Absolutely, it does. Yeah, and I'm going to show you how we get that. Yeah. It's an incredibly sensitive to that. Okay, so just, and this, there's a bunch of numerical models behind this, which I'm not going to have time to get into. But to get at those ecological parameters, I call them, the rate of new material being added and the rate that it goes away, one thing we did was to put in cores and carbon date the peat. So that's back to what you're asking. So we know the carbon dates all up and down the peat. It's useful for knowing when it began. It's also useful for looking at where it's no longer growing. So one of the results that we find everywhere is that around the perimeters of a peat dome, you get really old stuff right at the top. It stopped growing. In the middle, it's still growing, and you get a nice linear decrease in age as you come all the way to the surface. So here's an example of that. Here are a bunch of carbon dates, and we have a numerical model that solves this whole peat accumulation and loss thing, which is a whole nother conversation. But the two adjustable parameters in that are these ecological parameters. So we adjust them until we hit the carbon dates. So each one of these lines here you can think of as the surface of the peat perhaps thousands of years ago. So these are paleo surfaces of the peat, and we run it up until the current surface, and of course try and match that as well. So we do a good job of hitting, in the model, hitting the measured ages of the peat. There's this interesting little offset here, which has to do with the fact that these tip-up pools are forming everywhere and making the peat in the top meter or so younger constantly. And then I showed you this plot before, but I didn't tell you what this line on is. This is the line from the estimated parameters, and this has got to be pure luck. It goes straight through the very difficult, somewhat sketchy to estimate methods to get this relationship. And the important thing here, so what this says is that only when the water table is above whatever it is, 5 or 6 centimeters from the low spots, do you get accumulation. So what you see is a lot of loss when it's down here. But remember, the water table hangs out right here most of the time in a healthy natural peatland. In a drained peatland, it's down here, right? So you're losing tremendous amounts of peat. Another sort of outcome of this, if you go into, and I've got the reference here, into sort of the old peat morphology literature. There's debates about whether peat starts as like a little peatlet in one spot and grows like, some sort of blob over the landscape, or whether it sort of starts as a big flat thing and then just sort of bows up like that. But what our results indicate are that it grows like this, sort of pancakes that just pile up on top of each other. Okay, the exception that proves the rule. So remember, this guy is not hanging out with all the other ones. So in other words, at that spot, the water table is a bit higher. There's more puddles available to fall in at the surface. So what's going on there? Well, that happens to be one that's located here, okay? And it's above this line where there's a break in the Laplacian. And so this area of the peat dome does not have the same Laplacian. So if I told you it had uniform Laplacian everywhere, I was sort of lying. It does, but it's growing, right? And that's why it doesn't have the same curvature yet, because it's in fact wetter and growing. Yeah, so I think that's kind of a cool little, let's say exception proves the rule, kind of a cool little beautiful thing. This is hard to see. It's hard to even tell it's there. It just means that there's a few more centimeters of water down in these nooks and crannies and all. But that ends up explaining sort of the ecology, the formation of this peat dome, which you see at a much, much larger scale. Just a couple centimeters difference in the water table. Yeah?
Just to, can you go back to the previous slide?
I can try. Yeah.
So you're saying the side slopes, the stable part is closer to the river, and the growing part is on the top, but the water table is higher on the hillslope?
It's higher, but it's flatter.
Okay.
So it's not draining as much.
Okay.
So it's wetter uphill than downhill.
Okay, just because, could you get that from the steady state Buchanesque solution, or are you saying that this is a transient?
This is a transient thing.
Okay.
Yeah. So in fact, we run that transient model. Really, we can only run it up until it becomes steady state here.
Okay.
Yeah, you're absolutely right. It's just sort of, it's easier to explain it in the equilibrium sense and then back off and try and do the, or maybe the transient is just frightening to me. It's so much, there's a lot of really interesting numerical challenges and things, which would be a whole nother talk. But yeah.
And it's the transient in the groundwater solution, or the transient in the...
So in everywhere here, the groundwater is incredibly transient because it's raining and not raining.
Yeah.
It's transients in the peat surface elevation. So everywhere down here, it's not moving at all. And everywhere up here, it's growing in this simple case. In other cases, there's this crazy transients where it kind of grows in one place and that kind of redirects the water, so it gets hard to understand how it works. And these complicated cases are the ones that we need to understand how to manage canals and drainage. Is that, you got it? Yeah? Okay, so I think I have 3 implications of this that I would like to convey to you. The first is a very hydrologic thing. So I thought this was useful here and to connect to previous talks. And that is that we can get the parameters, the hydraulic parameters that describe everything about groundwater flow in the system just by looking at the hydrographs. We don't need a model of groundwater flow. We don't need a Tice solution or any kind of model. We don't need to do a pump test or slug test or anything like that. So what I'm just showing here are I already showed this, but basically this process of moving these things around until you find, and here it's not, I'm sorry, it's not in water table. Oh yeah, no, I'm sorry, this is totally right. So this is the jump for a given storm depth. And so I'm calling that dynamic storage here and showing how basically it's not linear. I'll talk a little bit more about the shape. It turns out to be important. And that's the rising limb, but not against time, against water added. And then the falling limb, we do the same thing and move them around and get this.
Harvey,
Yeah.
can you tell us a number about what's the annual precip, how often it rains, and
Yeah.
the ET?
So it rains more than once a day, not quite twice a day on average. There is no really serious dry season, and but yeah.
Total is like what, 1,000 millimeters a year? Or?
Oh gosh, what is the total here right now? I'm kind of blanking on it. It's about, let's say, in the order of 2 meters a year. So it's not as wet as some places, but it's wet enough. Yeah, okay. So anyway, so let's go, here's our ODE again. When you have a big rainstorm, and let's just pick the ones that are really big, we can forget about discharge during the rainstorm because that's slower than the accumulation of water. And remember, this term actually turns out to just be discharge. That's what it is. Because this, remember, is a constant at this point. So we can forget about that, and we can write that the storage specific yield is just equal to Q over delta T over delta D. This is delta D over delta T, so we just have to take, so the slope of this is 1 over the specific yield. That's probably the worst way to describe it, but the point here is that the specific yield is bigger up in this region, so the same addition of water creates less of a rise in hydraulic head. Here you have fewer or smaller pores that are for some reason filling and draining, so a given rainfall will create a larger change in the water table position. So we can get the specific yield, get that one parameter out of that. We know that, and now let's come over here and put everything else back together. So Q here, when it's not raining, is just the ET. And we can estimate that other ways. We can do it from the eddy flux tower. It's really not that bad just to do the thermodynamics of it. We know that pretty well. We know the Laplacian. Okay, so now we can take the change in the depths of the water table over time to get the transmissivity out. Right, and that is what we have plotted here. So we can get both of these hydraulic parameters, which is everything you need to model groundwater flow in here, out of just these observations. And what do we get? Well, for specific yield, something like this, it goes from maybe 0.1 down to the meters deep, and then at the surface, and actually we need to keep going for really big rainstorm events. It maxes out at 1, right? It goes to 1 all the way. And then for discharge and transmissivity, we have the same plot because the offset, the factor difference between them is just the Laplacian value. And this is a log scale. So when the water table is high, this blows up. It's huge. It's still Darcian as far as we can tell, but you get into situations where there's puddles and water flowing kind of along the surface, but then through obstacles and through thick plants and fallen logs and things, it remains Darcian. If we differentiate that, we can get the hydraulic conductivity. Now, point I want to make here for this group is, people talk a lot about scales of hydraulic parameters. What's going on here? I got these from looking at the behavior of the system. What if I want to go and just measure something directly? I kind of mentioned this. What if I wanted to take a core back to the lab and do a Darcy column on it? What if I wanted to do a pump test or a slug test? What could I figure out? And I think the answer is they're useless. Because the heterogeneities on the scale of meters, 10 meters, you would have to be a giant core to take back to do. And the variability here is on the scale of centimeters. with the where you are in it vertically. So what I'm saying is the horizontal heterogeneity is large scale, but the sensitivity to the vertical distance is exquisite, you know, just centimeters, and it changes. So anyone could figure out some other way to measure it, that'd be great. Let me know. But I think it's a good, I think this is as good a use of these concepts of specific yield and hydraulic conductivity as anything that you hear here, but it's just very different. It's exquisitely sensitive to the vertical movement and then has to be averaged over large distances in the horizontal. Did I see a hand somewhere? Vague. No, okay. Okay, a second implication is that now that we have this concept of the uniform Laplacian, we can figure out what the equilibrium carbon storage is in any pattern of drainage. And what that is it's a product of what I might call climate ecological parameters, the carbon density of the peat, so the carbon per volume of peat, and this Laplacian, which is a function of, as we saw, rainfall and all kinds of other things, times geometric. So the carbon storage increases with the square of the area, and then something that we call the shape factor here. And what that is that if you were to have a circular dome, which is kind of ridiculous, it would imply a circular river around it, you get the domiest dome within that geometry. So this is a large value. If you had a long, thin string of peat, it drains very easily, and this shape factor, yeah, it's something similar. You have to solve the Poisson equation, but for different boundaries. But it's very similar to the area over, or the square root of the area over perimeter kind of measure.
The shape factor is the units of length or what? So you have to have volume at the end.
Oh boy, I got to think. So this has units of 1 over length. Does it? Or 1 over, yeah. 1 over, I don't know if I can do this in real time. This is mass. Yeah. Yeah. I want it to be dimensionless. It is dimensionless. It definitely is. Yeah. And there's a little bit of a story to that. We basically normalize it by the amount that's stored in a circle. Yeah. Okay, so let's take, it's a super simple thing. Let's take a peat dome that is somehow inside a square, and we put a canal in the middle of it, and we cut it both ways. Now we get 4 little domes. You've now lost 75% of the carbon at equilibrium. And then we can apply this with the shape factors and all to what we see. So here, if we look in our area here, here's where our dome is. And remember I said the Malaysians cut down the forest on the other side. So here's our area and the domes. They cut down the forest and put in this grid of canals, which create very small areas with terrible shape factors. See why it's a terrible shape factor? This drain, for the same area, a long thin thing, I already said that, drains really quickly. So what we can look at here, shape factors turn out not to be such a big deal as area. So here's sort of bounds of reasonable shape factors and the parcel areas. And here is where we were with about 10 to 100 meters of peat. How did I do this? Meter. I think I've got a unit problem here, maybe. No, but
Volume per area, so you get just 1 over meter.
Yeah, 1 over meter.
Should be meter.
Yeah. Okay. So the point here is that you get orders of magnitude more peat, i.e., more carbon, than you do in Baram, which is the area that's been dissected by lots of canals. Okay. How am I doing on time? Someone?
30 minutes including questions.
30 minutes. I may skip this. You guys are so excited about this, I want to skip. Check your watch. Okay. Another interesting question, that was sort of a spatial thing. You know, how much does the volume of carbon depend on the spatial domain. But rainfall has really different temporal patterns. So it's an interesting thing to ask how much peat there is under different rainfall regimes. And so what we're looking at here is relative amounts of carbon or peat stored in a peat dome for different mean rainfall rates and different interstorm arrival times. Okay, so the interstorm arrival time at our site here is a little bit less than half a day. And Danny, I'm sorry I gave you the wrong number here. It's actually something more like 2.5 meters rather than 2. And what kind of rainfall statistics or rainfall time series do you think would make the most peat?
Uniform?
Yeah, if it just drizzles all the time, then you're over at this axis. Your rainstorms, there's just no inter-arrival time. And so you get the most peat. But so obviously as you increase the amount of rain, you get more peat. But as you increase the duration of dry periods, you get less and less peat. And this is all to do very much with the transmissivity function. You spend with few intense rainstorms, you sort of spend a lot more time with a high water table, or not a lot more time, you get a lot more flux with a high water table, which is actually that sort of mathematical way of putting what's obvious, is that when you get a flood, the water flows off quickly. And then we can also look at, here we have looking at larger time scales, annual amplitudes changes, and changes in sort of, decadal, 8-year kind of time scales. And this is interesting because some climate models, I don't think we really know, suggest that these amplitudes are going to get, this is the amplitude, it's going to stay the same 10 years or whatever, but the amplitude is going to get bigger. And if that's true, we'll lose half of the peat just from climate change. But losing half of the peat, that's good, that's nothing. We're losing all of the peat because it's drained. So I don't want to get too excited about modeling the effects of climate change on the peat because it obscures the fact that all the forests are cut down, drained, and it's just going away as fast as it can regardless of the climate. Okay, how about the rest of the world? So we didn't think this was necessarily going to work everywhere else, but we got LiDAR data from peat bogs all over the place. Now, none of these are like ours. I shouldn't say that. But most of these are sphagnum bogs, right? So the kind of bogs you see in Northern Europe or Canada. So we get that LiDAR data going all the way from really like 60 degrees north down to, this isn't as dramatic as it sounds because the climate starts to become the same down here in New Zealand. But anyway, across all of the latitudes of the Earth. And then from those LiDAR data, we can make plots of the measured surface elevation versus the sort of predicted surface elevation by solving the Poisson equation, the uniform Laplacian. And it's looking pretty good. And if we look at a whole bunch of them here, arguably the worst is our site. So it works so I want to make a couple points here. It looks pretty good, right? It looks like the theory applies elsewhere. Also, the scatter is really small, right? We could get a nice linear thing everywhere, but with more scatter. But that's not, for this kind of thing, that's not even much scatter. Scatter is really small. And the great practical implication of this is that these satellites that fly around and produce bands of surface elevation measurements, we can take one band across a peat dome and get this relationship and then know the surface elevation off of the band from that, so we can get the whole volume of the peat from one cross-section, satellite cross-section across it. So we just published a new paper where we actually develop a whole function, sort of we call it the bog function, that makes all of these things straight. And it accounts for the fact that they're not in equilibrium, for differences in vegetation from the edge to the middle. And then, has anyone heard of the Grzynsky potential? This is an interesting groundwater thing, sort of analytically hard to take in, that enables you to transform nonlinear transmissivity times the, in the Boussinesq equation into a new kind of potential, which follows the Poisson equation. But it is a potential in all the senses water moves from high to low. And anyway, we relate that to this, but I'm not going to have time to talk about that. But there may be some groundwater flow nerds out there that dig into this. There's probably stuff we didn't figure out, but we just published that recently. Okay, so I think I am going to make through this. This is a relatively short section that I didn't mention because I didn't know if I was going to get to it. I still have time, right?
Yeah, 20 minutes.
Oh, I'm doing, wow, how'd that happen? Okay, let's talk about the Grzynsky potential for 10 minutes. No, I won't do that. So I want to make an argument here that peatlands in general, tropical peatlands are what I know, are a reasonable place to go to try and reduce greenhouse gas emissions. One thing I've realized I haven't had a chance to talk about, invite me back next time and I'll talk about all the methane emissions and methane cycles. There's an interesting, the same way this uniform Laplacian kind of makes everything, I think, sort of elegant and simple, there's something similar going on for methane, but it's different. But all I can talk about here, well, let me just say, there is an issue that when you raise the water table, of course, you have less oxidation and less CO2 coming out, but you in fact have more methane. So there's a little bit of a trade-off, and you have to, it matters, it can matter. You have to think about that. But I'm just going to talk about the CO2 emissions here. And the three reasons why I think this is a great place to work on this. I'm not arguing for the importance of carbon credits or carbon trading. I'm just saying if you have good intentions and you want to reduce CO2 emissions to the atmosphere, this is a good place to do it. So right now there's huge carbon fluxes going to the atmosphere, and there's huge amounts of carbon stored per unit area of land. Now, I've talked about Southeast Asia. Over the last decade, it's just been discovered, which is kind of remarkable, discovered that there's enormous tropical peat swamp forests in Congo. There's other ones in Central and South America. And in all of these, they're solid organic, they're organic carbon to serious depths. There are reliable methods to control this flux now because of this, the water table, the relation to the water table. I like to think of it as a hydrologist. You can explain to people who aren't hydrologists, we can turn a knob. We can move the water table up and down. And we know what that does with this theory. And we can verify it. So let me just say a little bit more about all of these things. I stole this from the literature, and what this is showing is the amount of the density, the amount of vulnerable carbon per unit area of land, and over here, how fast that's going away right now. And tropical peatlands are out here. It's an enormous amount of carbon going away very fast. Okay, this turn the knob thing. Let me just give a couple examples here, and there's a lot more to be said about how you design canals and things. One simple example, one thing I see there is that because the peat catches on fire in these terrible fires, people put in fire breaks, which just means digging a long ditch that fills up with water. And then if you have a fire on one side, it can't get across the ditch to the other. It's kind of dumb. Does anyone see why this is just obviously a bad idea? Yeah, the ditch drains the peat, and all the fires are ignited on the edges of the ditch, and they wouldn't have been there if the fire break wasn't there. A similar thing with roads. So when roads are built on top of the peat, there's always ditches next to them that keep the roads from flooding, and then those ditches lower the water table around the road. The peat oxidizes, goes away. The road shrinks, not uniformly, because there's huge logs underground. The road gets incredibly bumpy and collapses. And the ditches keep digging deep, going deeper, and fires are caused by people laying their motor scooters just on the ground next to the road. The carburetor touches the dry peat. It's terrible. Well, what about some simple things like put in shallower ditches that would only fill with water when there's extreme rainfall events that would flood the road? Yeah, so that kind of thinking, I think if it were used in road construction, used in the palm oil plantations, you may not turn off the CO2 fluxes, but I don't think they have to be so big. And then the accurate ways to measure it is just that because the peat is entirely composed of organic carbon, we don't have the issue for soils in agriculture and across the world of trying to figure out how the carbon content of the soil changes over time. Always all carbon, right? So this bedevils all sorts of ideas for changing agriculture and all, because you have to take cores and it's just a big mess to figure out how much carbon is there. Here we can measure the land surface and do an awful good job. We still do need to understand if there's any compaction or not. So just with LiDAR, with some of the new satellites, might be good enough to do this at a small scale. We can actually see how these carbon schemes work. So yeah, just a couple closing thoughts, not anything I haven't said. First thought is kind of, is just that sort of surprising thing that this coupling between ecology, call it ecology, and hydrology actually leads to a system that is simpler to understand, that can be described by differential equations. That's my observation. If you tried to come up with these sort of general understanding of a mineral soil where there's all kinds of crazy things going on, well, good luck to you. But here it's that coupling itself that kind of enabled us to write it, to do the Poisson equation. And then the sort of second observation is hydrology. The kinds of things that we do here have a role here in controlling the carbon cycle. It has a role everywhere, I'd argue that. I mean, absolutely. But here the role is straightforward. We really, we understand the water table, and if you move the water table up and down, you change the carbon fluxes. So one more thing, totally different. I'm giving, I can't believe, another lecture today. And, two more things. I'm sorry, my talk is over. I'm now moving on to administrative stuff. Another lecture at 4 o'clock on a totally different topic, the policy and economics of geologic carbon capture and sequestration. So anyone interested in that, come here, and anyone, we will insult each other. I have strong opinions about this, but it'll be fun. And then I realized another announcement I would like to make is, this is a great group to do this to. I have positions for 2 postdocs now, not to work in Borneo, but to work on peat and marshlands, both on the, if anyone knows it, the Plum Island Long-Term Ecological Research Center near Boston, and then another one in the Harvard forest. Thank you.
On a bit time for discussion.
So trying to maybe tie the two together, like, is there any work being done on trying to restore some of these degraded peatlands?
Yeah. We actually have a place. So it's like 10 years ago we were first there. A massed fruiting event occurred which is this interesting thing where every so often, it can be 30 years apart, the trees all produce their seeds. So we were able to collect a bunch of the Shori albida, those are the big trees, their seeds, and we grew them in greenhouses, and we've got next to a road, actually the road I showed there, have been planting them and nurturing, trying to figure out how to do that. Right now, I don't know of any case where anyone has gotten the natural, what do you call it, the indigenous vegetation trees to regrow, which is kind of interesting, kind of mysterious. It's very hard, even in the forest, to find any young tree. I don't know. But yeah, so we're doing that. And there's all sorts, and the biggest, simplest risk is that fire could come through and destroy it at any time. But hopefully it won't, and we'll get more data. Yeah.
When working with ecological systems, a lot of your math, at least at the beginning, was based on this assumption of steady state versus transient. Mm-hmm. Do you have any issues assuming steady state in environments that are often in constant flux?
Yeah. So when I say, I hedge on the word steady state and equilibrium. I mean, the water table is moving up and down, the trees are falling down, all of this is going on. The steady state is the position of the land surface over annual time scales. And so that was really an observation, that we found this uniform Laplacian and we tried to understand it. And so in a sense, it's an observation that it's at this steady state. It's neither growing or shrinking again. Now, when you put a canal through, the land surface, starts to collapse. It's totally not at steady state. But it's sort of important, like what is at steady state or equilibrium? I would never say, certainly locally, nothing is, and everywhere the water table is going up and down all the time. But under some conditions, the time smoothed land surface stays the same. The curvature of it as well, yeah.
Charlie,
Yeah.
steady state related to that. Your peats are about 3,000 years old. Roughly.
Yeah.
You assume some rates of growth. Mm-hmm. Okay, so that takes care of the water, the carbon, and the light. What about nutrients limitation? I should expect something to kick in after a few thousand years.
Yeah, I think so. And it's another, so there's interesting sort of models that we start making the nutrients. We're going to have to close down this field site soon, but I don't know if we'll get there. But, couple interesting things there. First, it's interesting to model the fact that the trees and the logs themselves hold on to nutrients for century time scales. So that kind of slows down the loss of nutrients by flow out of the system. So that's important. Now, some nutrients, particularly phosphate, must be diffusing up from the underlying marine clays. That's the only explanation, and it's certainly the case. We see gradients that would be strong enough for back diffusion up into the peat. And that will work to provide phosphate for the plants when the peat is thin enough. But once the peat has grown really thick, you've got a much longer distance to diffuse. And I don't think it works, and there's always more details, but if we go to older peat domes that are bigger, the central part of the peat dome starts to have sort of dwarfish trees, what they call carangus there. And I don't know, but my explanation is that the peat's really thick there and really old, and it's no longer getting a sufficient flux of nutrients from the underlying clays. Yeah.
Hey, Charlie, one quick question. Going a little bit outside of the peatland,
Yeah.
Do you have a chance to measure how much export of VOC you have to the rivers that are surrounding the...
Yeah, we have a lot of other people have done a really good job of that. There's people, if you want quantities, I can't give it off the top of the head, but the water is always like 60 milligrams per liter. It looks like coffee. So yeah, there's a lot. I think the Kapuas River nearby is the river that delivers the most organic carbon to the ocean of any river on Earth. Yeah. And the rivers are anoxic. There's enough in there that even though they're turbulent and all that, yeah.
So the classic steady-state solutions to the Busanesque of the dike problem and the circular island problem
Yeah.
give a parabolic profile.
That's right.
they're based on a constant conductivity with depth. Can you contrast what is the difference between your parabolic solution compared to
Yeah. So ours is simpler in the sense in that we actually have a uniform transmissivity for any given depth. So it's actually simpler. It's closer. If you do the steady state, it's kind of closer to linear than what they did because we don't have flow through the. I mean, that's the reason we went and looked at other places and all, because we thought, well, some places there's going to be more flow in the middle of the dome because there's more thickness for which water to flow. But the top is so much more conductive. The little bit of flow in the bottom doesn't really matter. So it gives a slightly different answer. It's parabolic. I think that solution is, I forget, it's like a square root in there. Yeah. Does that answer? Yeah.
Enough for the moment.
Yeah. And there's some old peat literature which explains the shape of domes with just that. Yeah.
One other question. How far above sea level are you?
Not very far at all.
Do you have potential issues with changes in sea level changing, the groundwater system, the boundary conditions?
Yeah, it's a little bit of a race in a lot of these peatlands for how fast they're decomposing and how fast sea level is rising. And they are decomposing. The land surface is coming down maybe 10 times faster than sea level is rising. But they're close to sea level, and once you get close enough, then you're going to have all kinds of salt water flowing in and high tides and things like that. But it's another case where it's a little bit, I am an absolute, we got to stop climate change advocate. But I get in this kind of funny thing where people want to talk about that. And I'm like, no, they're all burning. They're on fire. They're decomposing. Sea level rise is not the thing right now. Yeah.
Maybe one last question.
So yeah, I will have a quick question. So with the global CO2 rise, did you observe, maybe from historical, that is there any increase in carbon?
Yeah. Is there any CO2 fertilization? I wish I could answer that question. We don't have the data in any way to address that, I don't think. But it's a good question. Yeah. People know what he's talking about, so I don't much. We have more CO2 in the atmosphere, so we actually have more photosynthesis because it drives the reaction. It gets complicated, but it drives the reaction toward. And so it'd be nice to know. And so a really fascinating thing is we know that the land overall on Earth is a big sink of CO2 from the atmosphere right now. I find this astounding. It accounts for a lot of the emissions we have. But we don't really know where that sink is. And maybe that's where you're driving at. We know it for a few sort of temperate areas pretty well, but in the tropics, we have no idea how big or small or where the fertilization effect is. And it's really important for understanding the current carbon balance in the atmosphere.
Thank you. Thanks, Charles, again.